Are you ready to venture into new territory? So now we're going to do, we did a one-tail hypothesis test for the population mean where the population standard deviation was known. That was up here, one-tailed hypothesis test for the population mean where the population standard deviation was known. Now we're going to do a two-tailed hypothesis testing. We're going to do two-tailed hypothesis testing of the population mean where the population standard deviation is known. So went from one-tailed to two-tailed. And so here's an example, and this example has 2 slides to explain it. And I think, just to make this a little bit more clear, I'm going to bring this up here, and I'm going to grab all this stuff here, and Control X, and then I'm going to put this here, Control V, and then I'm going to select this whole deal. And where's the bottom of my slide? It's like right there, so it just locked in. And now it's all selected. I'm just going to bring this down to like 18. And I could be a little bit bigger even. I can't go to 24, that's too much, but we'll stick with 18, that's fine. So I think that's just like a lot easier, and then we could delete that. So now we have it all on one slide. So Max Flight produces golf balls with a mean driving distance of 295 yards. Its quality control program involves taking periodic samples of 50 golf balls to monitor the manufacturing process. Quality assurance procedures call for the continuation of the process if the sample results are consistent with the assumption that the mean driving distance of the population for the population of golf balls is 295. So we'll just highlight mean population. And otherwise, the process will be adjusted. Assume that a sample of 50 golf balls provided a sample mean of 297.6 yards. The population standard deviation is believed to be 12 yards. Perform a hypothesis test at the 0.05 level of significance to help determine whether the ball manufacturing process should continue or be stopped or corrected. So the first thing we want to do is do our hypothesis test. And so to do that, I can't really adjust those because they're images. There's no typing in them. But I'll just bring this down here. And I guess I just need, well, I'll do this here. So copy that, and then I'm going to do this here and get rid of all this. Whoop. And then here I'll put hypothesis. And what did we call it up above? We called it develop the hypothesis. So we'll get that. Develop the hypothesis. So we'll do that, and we'll do this here. And paste develop the hypothesis there. That looks a little bit too big. And so our hypothesis will be the null. The null will be that our golf balls have to be, right? So we want them to go 295 yards. We don't want them to go more. We don't want them to go less. Like if they go more, customers will be happy. But then like the golf people who run golf games will be like, you're making balls that go too far. And they're not acceptable for tournaments. And if we make them less, customers will be unhappy if we make them go less. So we got to keep them right at 295. So null is that the population mean is equal to 295. That's just my guess. And alternative is population mean is not equal to 295. And that exclamation point is like syntax in programming. That's what it means to me. And that's not necessarily statistics. I'm just going to leave it. But I guess I could put a little note down here and just say not equal to 295. Okay? Just so if anybody comes across this, they're like, what is going on? What's that? And that's maybe a little bit more jargon. I'm super familiar with it though, so. And I think it works. So not equal to 295. I just don't know how to insert a not equal to sign. I'm sure there's some way to do it on the keyboard shortcut. Or, not equal, and I could do that, and then I could grab this one just right from here, Control C that, and then I could come here, and I could just go Control V. There we go. That works. That's pretty cool. So that's my null, and that's my alternative hypothesis. And we'll just put these two together, just so they're a little bit closer. And we'll make that bold, and we'll make that bold. All right, that's the first step. And then the next step is going to be to gather all of our information. And to gather all of our information, I really kind of like this slide here, right? And I'm going to copy it. And I'm going to bring that slide there down to here, right there. And I'm going to copy this right there and get rid of this one and delete it and then put that there. And I don't know if we need those. I'm going to get those out of there. And then the next thing we're going to do is open this up into two windows. And I think I might already have another window open. I'm just looking here. I don't want that one. Close that. All right. And so now, because actually, I guess that would have been good because they update. They update simultaneously. I'm just mumbling. And now we want our problem. Here's our problem. And we can start to gather our data. So here's our hypothesis null, right? Our null. And I think I'll just make this bold. And we'll get rid of that. And then here's our alternative. And we'll make that bold. And it's the population mean is equal to 3. And then the population mean is not equal to 3. And so I could just go copy this again here. Whoop. And put it here. Not equal to 3. And then the alpha, the level of significance on this one is 0.05, right? 0.05 level of significance, which means our confidence coefficient or our confidence level is 95. And our sample size is 50. And our sample mean is 297.6. And our population standard deviation, I think they gave it, is 12 yards. 12 yards, right? So right there, population standard deviation. So now knowing all that stuff, we could calculate this right here. And so what are we looking at? What are we looking at? I don't think we need to see this anymore because we got all this data. So I'm just going to close this slide and just make this bigger so we have more on the screen. There we go. So our sample mean is 297.6, 297.6. I'm just going to highlight that, and we'll bring this over a little bit so we have a little bit more room and everything's not cramped. 297.6, 297.6, 297.6. And then our Z, and this is a two-tail, right? So we're looking, is it too small or is it too large? We want to see if it goes out into those ranges where it was too big or too little. So it's two-tailed. And our Z at 95% will be 95% in the middle, and the alpha will be 0.05, and 0.05 between each tail is 0.25. It's 2.5%, so it's 0.025. And so if we have 0.025 in the top right tail, just to look at this picture, 0.025 in the top right tail, that means that 2.5% of our data is from here over to the right, and 97.5% of our data is from here to the left. And since Z-scores are from here to the left, we're looking for 97.5% of our data from here to the left. And so we're looking for 97.5, and we're at 97.5, and so it's going to be 196. 196 is 97.5. 1.96, that's the number. 1.96. And so I need to come back down here to the green, and it's going to be 1.96. And that is the number, man, for 95% confidence and two tails. It's 1.96. I'm going to highlight that, Control-C that, and put that here. And then we have our population standard deviation, which is 12. And it's going to be divided by the square root of 50. And so when we do that math, what is the square root of 50? So calculator. And I'm going to do, that's so weird, it's such a big calculator that way. I like it better this way. I'm going to do 50 and do square root, and it's all of that. Can I copy that? What's this? Keep on top. I just want to copy it. There we go. We'll do it to like 711. We'll just call that 11. So that's going to become all of this divided by 12. So it'll be that. and that'll be 12 divided by that. Whoop. And so we can come back over here and we can clear all this out. We can say, hey, 12 divided by, and then control V. Cool, that worked. And that gives us that number. And we can just add this line in once more. Boop, right here. Just add one more. And so that's going to be this number. So we'll copy all that. And we'll do it to 7, 1. We'll do it to that. And so that's going to be all this. And then when we multiply that by 1.96 times 1.96, that's going to be equal to this. So I'm going to copy that, 3.33. Well, let's call it 3.33. 3.33, right? Because you can round that 6 up, make that 2 or 3. And then when we look at that range, we could say that we could do like what? 297.6. I'm just going to clear this. 297.6 minus 3.33. And that's going to give me 294.27. 294.27. And this will be my confidence interval, or interval coefficient. No, confidence coefficient. It'll be my, oh wait, no, I want my confidence interval or my interval estimate. I'm going to come back down here. And 294.27, and then I'm also going to do, clear that out. I'm going to do 297.6 plus 3.33, and that's going to give me 300.93. 300.93. So with 95% confidence, we could say that the population mean is going to be between these two numbers. And we're really looking for a population mean of, according to this, 295 yards. 295 yards. And, 295 yards. That's what we're looking for. So with 95% confidence, we could say that, it's between those two. So we're just barely legal, right? Like we made 295 by like less than 1. So that's pretty tight. And, if you want to have like the best competitive golf ball that goes the farthest and is still, like tournament legal, maybe this is the way they play it. And so that's what I get from doing this confidence interval. So now to calculate this next one, we'll do the next one in the next video. See you in the next video. Let's go do that in the next video.